Now, as our second example, let's start with the column vector 1, 2, which again lives in R2, two-dimensional space. We see a picture of it, again, the pink vector. But now, consider every possible linear combination of these vectors, meaning all this vector multiplied by every possible constant. This is what it means. The linear combination of just a single vector. The end result is just this line in blue. So the line, the set of vectors, is the span of this set with just one vector in it, the 1, 2 vector. In general, any element in vector that starts at origin and ends up in this line has the form a, comma, to a, where a is any real number. And how do I know that? Well, I know that the span of 1, 2 is a times 1, 2. So I get a to a as the form, which written horizontally looks like this. So looking at this picture, there is something very important that we already seen in the previous example, is that within this span, the zero, the origin, is always an element of this space. So the line contains the origin, just like the two-dimensional plane that we saw in previous example also contains the origin. You can see this because if I set a to 0, you get 0 times 1 and 0 times 2, which is 0 and 0, meaning the origin. So the origin is inside this span. So this is a very important property that we'll see over and over again. So, again, this line constitutes a vector space. And the reason being, any vector that starts at origin and then it's somewhere like this, and you have a second vector like that, if you sum these two things, you still are along the line. So any combination is always an element of the line. So the line is closed under linear combinations of its elements. So it is a vector space. But notice it's more than a vector space, because it's also a subset of R2, the entire plane that you see here, this entire thing. More than just being a vector space, it's also a subspace of the entire plane. So these two examples that we saw previously motivates us to introduce the following definition. A vector space is a set of things which is closed under linear combinations, just like the plane or this line. But a vector subspace, it is a vector space, but I need to add something to it. A vector subspace of a vector space, call it A, for example. In this case, a vector subspace of A is a vector space which is a subset of A as well. Can you see? So this is very important because the line is a subspace. The line here is a subspace of R squared, the vector space that we saw in example 1.